Okay, hello everybody, and welcome to our first installment webinar for around our Microbit ecosystem and our Gator boards specifically. Um, my name is Derek Runberg. I'm going to be your host for these three. If you need my contact information, here it is. So my email address is the best way to get a hold of me, and then schedule phone calls if you have any questions later on. We will also be taking or be attempting to take live questions towards the end, so feel free to be able to ask those then as well. For those of you that don't necessarily know what the microbit is, we're going to go over it a little bit earlier. I'm hiding behind a PowerPoint presentation today, but the next two installments are going to be me in front of a camera and doing some building and demo of some of the boards and products that we're going to be talking about today. But today is just to get us acquainted with the Gator system. So we're going to take a look at both the Gator Bit as well as all of our Gator boards, the whole full ecosystem that uses alligator clippable circuit boards. And then we're going to look at and talk a little bit about what's next in the next two episodes. So to kick things off, if you've never heard of the Microbit is a really tiny computer. It's a small PCB. It came out of a project with around the BBC trying to get computer science into the classroom in the UK, where I think it's every sixth grader got one a few years ago, and it's spread ever since. The Microbit Foundation was born out of that project, and then we've been working with the foundation to help bring that to the States in a more prolific way in schools. A couple of benefits around the Microbit is that there's no software installation required. All of the programming is done through a web browser on a website, and there's no student Privacy Act information, all that stuff. There's no login. It is just land on a web page and you can start programming right away. It's programmable across all major platforms, Mac, Windows, and Chromebook. And Chromebook is the key to this, especially in the US in terms of education platforms. Can also be programmed with an iPad using the iPad specific app. This does leverage Bluetooth, so if you have a number of iPads in the classroom all at once, pairing, let's say, 20 microbits via Bluetooth is a little tough sometimes. So scaling that up can be difficult in a large classroom. The price point to get started is about $16.50, and that's what's called a Go Bundle. That includes a USB cable and a battery pack as well. And then it's scalable in terms of applications. And we're going to talk a little bit about how to scale beyond the microbit itself using the Gator Bit system today. As we've worked with the microbit over the past couple years, we've really fleshed out what our ecosystem looks like, both in terms of tools and products, using the different microbit boards and breakout boards, carrier boards, expansion kits, things like that for different applications beyond just what's on the microbit, but also programming environments. So MakeCode is our primary programming environment, but we do also support some Python programming as well. And it really spans across all skill levels. So going from that beginner and intermediate, even to some advanced programming with the microbit, using text-based programming, JavaScript, Python. It really has a really low floor and high ceiling when it comes to computer science hardware, programmable electronics in the classroom. A little bit of the hardware that SparkFun provides and sells and is developed around the microbit. Again, it's an ecosystem approach where we have individual themed boards that the microbit plugs into, and then we've developed kits that leverage those boards. And the Gator Bits are one of those things, or the Gator Bit and Gator boards are one of those things. And it's really been designed for the younger inventor, this younger student in mind, in terms of rapid prototyping, but with possibly little fingers instead of full-sized hands and needing a breadboard and things like that. So the alligator clips make it a lot easier to build and integrate into your projects than something like our inventor's kit for the Microbed. And our ecosystem of Gatorboards is growing ever so slightly all the time. We originally launched the Gator Bit and some of the original Gatorboard sets, I think actually a couple years ago, if not last year. And this year we've released our Gator Science boards, and then we're actually releasing currently, I think we released last week, our Gator Science Kit, and then we have a new kit that I'd like to announce today, coming I think in about a week. But these sensors over time will expand and make it more useful for the classroom and to integrate electronics without spending 2 weeks getting up and running. Some of the boards, the Gator Science boards specifically that you'll see today in the presentation, come out of a collaboration project. It was a National Science Foundation grant project that we've been working on with University of Colorado Boulder and the Denver Public Schools, where how do we get students really building their own instrumentation and using that instrumentation in inquiry-based science. And we've been the hardware partners on that NSF project, and these boards have come out of that research. So we'd like to thank CU Boulder as well as Denver Public Schools for their part in this and hopefully the future of these boards as well. Now I want to share a little bit a video interview to give you a little bit of that context and background of where these boards came out of in terms of the thought process. But we also want to just highlight this amazing project and this NSF grant. So I'm going to hit play and be quiet to let you listen.
This project is really important for the state of Colorado and the nation as a whole because we are looking at how to make learning computational thinking inclusive for all K through 12 students. Currently, most students who learn computer science and computational thinking in middle school and high school do it through electives. So these are optional courses that not all students take. And so we want to make sure that all students have access to this body of knowledge. So that's why with this project we're focused on embedding computational thinking into mainstream science courses that are required and that all students must take.
Most of our initial goals were surrounded by the adoption of next generation science standards in our state and how can we prepare teachers to transition to those. That was one of the big pieces. We also looked at teachers' lack of confidence when it comes to computer science, and so we really wanted to tap into that and build that, because oftentimes if they don't have the supports and the content knowledge, teachers are not willing to really teach it or dive into it, so we really want to develop those skills as well as create a professional development model for other teachers across the country to use what we did during this project.
We spent a lot of time brainstorming different phenomena that meet a set of performance expectations for the next generation science standards. And then, I think I went through the list of I2C sensors and other sort of sensors on the SparkFun website, and we went kind of back and forth being like, these are some interesting, phenomena that we've come up with that meet, a good criteria of performance expectation. These are the sensors we have, which ones kind of meet up and can provide sort of support for deep integration of computational thinking and science content. And then there's an additional aspect that we're trying to focus on sort of this place as a construct in the classroom, because one of the things that we hypothesize is that when kids actually get to sort of do investigations that are grounded in their school or in their local community, that hopefully will going to increase interest in underrepresented groups because it's a little more real to them and they actually get to go out there and do it. And specifically, we had done the first year with mold because the environmental sensor provides a lot of different things that you can measure, and so then kids were super into going around looking into their schools to be like, is mold here? Do we get to shut down this school?
It just allowed us to really tap into the science that we wanted to tap into in a new and kind of innovative way.
First of all, it's a partnership bringing together some of the industry, academia, and public schools with the ultimate goal of increasing kids' engagement at middle school level in science, computational thinking, which is really a form of computer science education, by bringing in all these kind of consumer grade electronics that are affordable, which is very important for a school district, are programmable in simple ways, and are mobile. And integrating that within the science curriculum to make science more interesting and to help kids begin to explore ideas in computer science, and thinking about that it can actually have an artistic dimension, that it can really help you ask deep questions about the world around you and help you understand the world around you. So ultimately, that's what we want, is we want to be able to engage middle school kids in science and computing. And that's where the SparkFun Electronics dimension comes in. And then working in the Denver Public School, which is one of the largest districts in the country, it has all kinds of different kinds of kids. And if we can make it work in this district, we have a good shot of making it work elsewhere in the country.
In the past, as a teacher, I've used, temperature sensors and the basic stuff, but it's at a different level when it comes to the data manipulation. And I think it gave us just a nice opportunity to explore the science really deeply in a wide variety of ways.
I just think it's a great idea using these sensors where students can collect their own data and they can own that data instead of just looking at something through a module or a simulation. They can go out, collect the data, own the data, and then design their own tools through computational thinking and learn that programming background on it. So it kind of serves all of that. And also I think if they can own that data, then they're going to be much more engaged in that lesson, and then they can apply it to real world problems that they are facing with either their family or their community.
For me, there's several takeaways. One is that kids in middle school can engage in science activities where they ask deep questions about the world around them, use modern scientific equipment and technologies to address them, and come to care about the answers. And that's an important and significant shift for how lots of science instruction has happened and continues to happen around the country. So I'm really excited about this shift to more what we call inquiry-oriented science. That is, where kids are asking questions about the world, and then using computing technology to begin to answer those questions in ways that don't exactly mirror what practicing scientists do, but have some family similarities, so that school science is not completely divorced from what real scientists do. That's the part I think would probably be the biggest takeaway for me.
Perfect. I know showing a video on a webinar is not always the best thing to do, but we're very, very proud of that project and what's come out of it. I personally was one of those students and teachers that was always hungry for real science in the classroom. And so to be able to provide that at some level has been really fruitful and amazing. And I'm just really excited to see where these things go and build more projects. And again, in the next 2 episodes, to be able to show and demonstrate some really simple ways that you can incorporate computer science and inquiry into one, and really embed this into your science classrooms and even something like a social studies classroom. But first, let's take a look at some of this hardware up close and personal. And we'll start with the heart of the whole thing, and that's the Gator Bit itself. A lot of questions we get is, why the Gator Bit? The Microbit already has some alligator clippable edges. Why does this thing exist? And one of the reasons is, yes, the Microbit has the ability to do some alligator clipping, but those pins or those places that you connect to tend to be very simple in terms of functionality. You only get, I think, an option of three pins to work with, where the Gator Bit breaks out almost all of those pins, as well as breaking out some more advanced functionality and power options in terms of what you or your students want to do. And so even though this is it makes the Microbit itself a little bit bigger in terms of a footprint, the functionality that you get with a Gator Bit is significant. Not only in terms of the Gator pins and the alligator clippable pins, but also some of the hardware that we've added on, so that it's an extension of the Microbit and allows your students that much more room to run in terms of what they can do with the Microbit. So first up, the general purpose inputs and outputs. So these are similar to the pins that you see on the Microbit itself in terms of pin 0, 1, and 2. But we've run it out from pin 0, 1, 2, and then I think we skipped to 8, 16, and then 5 and 11. 5 and 11 double as the button pins on the Microbit as well. So if you complete this circuit or close these circuits, it'll be the same thing as if you hit the A button or the B button. So it gives you another option. Instead of, if you wanted to use something else, another Gator board as that button, you can do that. These also double as outputs as well. So you can light up an LED. Pin 0 also is connected to a buzzer, which we'll talk about a little bit later, but these are the output pins as well. On the right-hand side, if you're looking down at the Gator Bit, is your power rail, your power center, your power strip. So we break out both 3 volts and 5 volt output for your power. We give you 2 ground pins, as well as whatever power or whatever voltage you're plugging into the input in terms of the barrel jack, we give you access to that as well. So if you're using kind of an interesting or funny voltage from maybe a wall wart or a battery pack or some other power source, that'll be accessible there. And that will operate at between 2.9 and 9 volts. So you can hook up, for example, a 9 volt battery there, and if you wanted to get 9 volts out for some project, you still could using that pin there. On the far left-hand side are advanced sensor pins. So if you have any Gator Science boards, this is where they plug in the I2C, pins 19 and 20. But we also break out your SPI, which is a different communication bus for different sensors that the Gator Bit uses. So these are your more advanced boards, and we'll be using those later on when we use our Gator Science boards. Smack in the middle of the Gator Bit are some addressable RGB LEDs, or you might have heard of them referred to as neopixels. There are 5 of them total, and they are connected to pin 12. So you can use this as a very basic bar graph, have things change color, turn on and off, all without having to add a bunch of LEDs later on. So if you wanted to have a sensor readout be visually present as a bar graph that changes with the value, let's say a temperature, it can change both color but also the length of that bar graph. So you can show kind of multiple pieces of data in a very creative and almost artistic way. Last but not least, in terms of what's on the board itself, a buzzer, and probably the most important part of having a buzzer in the classroom is a mute switch. One of the things I always talk to our engineering department about is if this thing's going to make noise, a teacher needs to be able to turn it off in some way, shape, or form. Otherwise, they'll be pulling their hair out and throwing the products out the window. So we give you a mute switch to be able to turn sound off if need be, especially if you're using pin 0 for something else, right? We don't want the buzzer making noise while you're trying to blink an LED on pin 0. So we added that for you. So we talked a little bit about this, but why the Gator Bit? The expanded functionality, easy to integrate other hardware into physical projects. So instead of having to physically figure out how to integrate just the Microbit, or if you're breadboarding, how do I get things off of the breadboard and incorporate it into a physical project? The alligator clips allows me to kind of put an LED where I want it. If I want blinking lights of a cardboard dragon, I can put those LEDs in the eyes of that dragon and use alligator clips to attach them rather than have to run wire in a very creative and frustrating way. Access to invention and prototyping at a younger age. So it brings that idea of how do I bring my projects to life in the classroom at my upper elementary school classes to life. So how do I bring my social studies, how do I incorporate computer science into social studies? And one of the easiest things is we all have done one of those shoebox dioramas. How do I make those things light up, move, or play sound? And it's a really easy way to incorporate and do computer science across the curriculum. One of the things that I like about it the most is that the Gator Bit makes power management for the Microbit a lot easier. I can plug in a battery pack. I can hook up a number of servos and run servos without having to worry about my running out of power or access to power on the Microbit. So it just makes it so that we can build more without having to do a bunch of fancy circuitry. Some Gator options. So a couple of things that we look at is alligator clips are wonderful, but still sometimes a little hard for little hands, students that, even who am I joking, right? Even I sometimes have a hard time alligator clipping things and opening those alligator clips. They get slippery sometimes. So we also have banana clips, which actually press really nicely into the boards and stay nice and solid. So both of those options are really good for the classroom. And if you're dealing with younger kids, the banana clips, no matter what the age, the banana clips are just a nice, clean way to hook up, and they tend to stay hooked up a lot longer as you move things around and get things situated. So what do we clip to the Microbit? I've been talking about all these Gator boards, and so we're going to go through the existing products one at a time for the most part. I'm going to be quick, so it's not going to drum on, but wanted to give you an overview of what all these products are. So the first boards that we released are these Protos Snap form factor boards. So they are individual Gator boards that are kind of grouped on PCB, and then you can snap them apart. First up is our Gator control board. So it has 2 buttons. So I press the button to close the circuit. So I would hook these up. I could replace buttons A and B with these buttons, for example, with an alligator clip. I have a switch, just an on and off basic switch. And one of my favorites to incorporate into some really interesting interactive projects is a reed switch. If you've never used a reed switch before, it's a switch that you can only operate with a magnet. So if I add the magnet, the switch is closed, and current will flow through the reed switch. If I remove that magnet, that switch opens, that circuit opens, and it's like turning it off. So on and off, but if there's a presence of a magnet on there. If you've ever used like door and window alarms, or door or window alarm sensors, for the most part they're reed switches. So it operates similar to that security system door switch. Next up is our Gator starter set. This incorporates 2 analog sensors, or 2 analog inputs, both a temperature sensor and a light sensor. And in the middle we have an RGB LED, or red, green, blue LED. And this is not the addressable RGB. This is a standard RGB where you analog write different values to a red, green, and blue LED that they all are combined in this single package. So you can students can start to color mix red, green, blue values, but it's like having 3 LEDs in one. So they can build a stoplight from one light, a number of different things. Have red indicate if something's too hot, have blue indicate if something's too cold, yellow's that Goldilocks zone of in-between state. Last but not least of these Protos Snap form factor boards is the LED, or the Gator color board. And this is a smattering of LEDs of different colors. So we give you a couple of white LEDs, a red LED, a yellow LED, a green LED, and a blue LED. And you might be wondering, what are those, the strips towards the top? Those are extra power strips. So if I need access to more, excuse me, I need access to more ground, or power, I can use these to expand the number of power slots I have or ground slots. So if I wanted to, let's say, power 3 or 4 LEDs, I can do that without too much fuss. So that's a really fun tool and good tool to have in the toolbox of your Gator boards. And a big reveal here, coming soon, is the Gator Circuit Kit. So about a week and a half or 2 weeks ago, we re-released our Gator Science Kit, which is all of our science Gator boards that have to do with science are in one kit. We're going to be releasing a similar one, but for these basic input and output sensors and Gator boards. And what this is going to be is it'll be a focus on literally building circuits and a focus on circuits. So, and using them in creative ways. So things like a basic circuit, what's a series circuit and a parallel circuit, and how do I use these components as a more of a STEAM, including that art side of things, and incorporating those things into projects. So again, like the dragon with the blinking eyes, or a car that has a turn signal that you can, depending on which button you press, a turn signal left or turn signal right. So I'm bringing a lot of those projects to life using computer science and electronics. This is your kit for the Microbed. Focus across that curriculum. Now jumping into the Gator Science boards, and what we're gonna do is we're gonna go through all these boards individually, talk about what data you can get from it and how they hook up, all that fun stuff. But each one of these kits, both the Gator Circuit and the Gator Science, will get their own episode in the next couple weeks. So this is a general overview. If you have some questions about specifics, we might be able to answer them at the end of this, but really, I think a lot of those questions will get answered in the coming episodes. Starting off, the Gator Microphone. So this is an I2C sensor. So again, it works off of those advanced sensor section of the Gator board, or Gator Bit, sorry. It has its own MakeCode package. So a lot of these Gator Science boards has its own set of blocks in Microsoft MakeCode. So you'll be able to open up an advanced setting, say I'm using this specific board from SparkFun, and the blocks are right there ready to program with. The microphone measures two things. It just checks for sound. So has the sound changed? Has something gotten louder or quieter? And that's a binary value. So I can use that with like an if statement. So if it's loud, do something else, do something else. But we also get an analog sound intensity level. So again, that's an analog value depending on how loud it is. So not just is it loud or not, or is there sound or not, but also is there a range? Is it louder than it was 5 seconds ago? We can use that value to do something with. We can use this to monitor sound levels. But one of the things that I like to use a microphone for is detecting presence of something. Because usually when something moves, it causes sound. And a lot of other ways of detecting motion don't always get it, but usually sound does in some way, shape, or form. So that's one of the ways that I like using a microphone. One of the things that's we need to be very clear about that this doesn't capture the sound itself. This is just looking at how loud something is. So if you're looking for something that you want to record somebody's voice and be able to play it back later, this is not that type of product. This is just looking at literally the intensity of that volume. So you won't be able to use this to record crickets in the evening or anything like that. Next sensor up is the Gator Soil, and this is actually an analog sensor, so you can use this with the Microbed on its own, or any of those general purpose pins at the bottom of the Gator Bit. Again, it has its own MakeCode package, and it measures moisture by reading the electrical current that's passing between the two probes. So it looks like a little hot dog fork. If I stick that into the ground and add a little bit of water or some type of moisture, current will actually pass through that soil or that substrate and we can measure that. And depending on how wet or how moist that soil is, there will be more or less current depending on things. One of the ways that we can use this sensor too is a shear water detection sensor. So if you're wanting to detect if the water has risen or if there's even water in a room at all. So if you wanted to say, let's say, water in my basement, I can actually mount this a little bit of distance off the ground. And then if I know that if there's a greater than 0 reading on this, that water has collected and risen above that. So if you're looking maybe looking at a creek and to see if the creek has risen, we can put the sensor above the water level a little bit, and then if that water rises and it comes in contact with those two probes, it will close that circuit, and in the end, the water's risen, and we can have the sensor alert the microbit to do something. Set off an alarm, for example. The Gator Environment. Again, this is an I2C sensor, has its own MakeCode package as well, measures a number of different data points here, and so this is a really good investment for the classroom because it does give you access to a number of data points, and it's like a little Swiss Army knife sensor. On one side of the board, it measures volatile organic compounds, or VOCs, as well as CO2 equivalency. So especially when we're looking at environmental science inside of a building, both VOCs and CO2 are a big thing, right? So when I paint a new room, all of that stuff that I smell from the paint tends to be VOCs, volatile organic compounds. So we can actually measure and get the air quality in different rooms in the school. And so being able to do environmental science indoors in the wintertime when it's either cold or rainy or just nasty weather outside, we can still do that and look at indoor air quality. We also have access to humidity, temperature, barometric pressure, and altitude as well. Again, atmospheric measurement, indoor air quality, using this to track altitude of something. So for example, if you were to put a Gator Bit and this sensor on a balloon, a tethered balloon outside, you can actually let the balloon up and you can see the altitude change and measure that altitude as that balloon goes up. And at the same time, look at that temperature change as it moves from ground level up to 100 feet, up to 200 feet. Same thing with humidity. So we can compare those data points. Gator UV. Again, I'm going to be a broken record. I2C sensor has its own MakeCode package. It measures both ambient light in terms of an analog value, how bright it is outside or inside, but also measures UV radiation. So we can compare the amount of UV radiation on a cloudy day versus a sunny day and have that either log that data and look at that over long periods of time, or program the microbit to react to something that, let's say it's high UV radiation. Maybe the microbit moves some type of cover over a plant or something like that where it'll shade it a little bit more. Gator RTC, and RTC stands for real-time clock. So the microbit itself doesn't know what time it is. It doesn't know what day it is. It doesn't know what year it is. So we have to, and most computers don't. Most computers have to either access the internet for that information, or they use what's called a real-time clock, which is what this is. And this is programmed by the user to say, it's January 2nd, 2019 at 3 a.m. in the morning. And then from there, it keeps track of time until you tell it something else, or it turns off, or the battery dies. So this is a way for us to be able to tell the microbit, give access to the microbit to an alarm clock or some time, right? Or I can say, okay, microbit, at midnight, do something, make a noise, blink, whatever it is, but it gives it access to a clock. So we can do that in terms of the functionality and triggering that something on at a specific time. But one of the bigger uses for this is actually using that data and that time to be able to data log accurately. Be able to say, every hour on the hour, starting at 6 a.m., track the temperature, and we will be able to actually correlate the real time and the temperature of that experiment. So the real-time clock is actually a big part of accurate data logging in the science classroom. The last sensor that we're going to talk about is the Gator Particle. Again, I2C sensor, make code package, and this detects changes in particles in the air as well as your blood. And what this sensor is actually, if you have a Samsung phone, it's very similar to the heart rate monitor you have on the back of your phone that you can use to get your heart rate if you use a physical fitness or activity app. What this is it looks at the slight changes in basically your blood cells changing in density as your blood pumps through your finger. So we can actually get beats per minute as well as infrared light readings from this sensor. It's a really cool sensor, especially if you're looking at health sciences in the classroom and send somebody to run a lap and then check their BPM and then run another lap, check their BPM again. So it gives some integration of that. The last board we're going to talk about that's not necessarily a sensor, it's more of a tool. It's not an I2C board technically, that's incorrect. It is a serial board. It communicates over our serial bus with RX and TX. But it's an SD card logger. So I can actually save data to an SD card over time. So I can build a project, let's say it's going to track temperature and light. I can go put that project out in the wild and have it log the temperature every 5 minutes for, let's say, 2 days. And then I can pull the SD card out of that and go insert that into something like my Chromebook or my laptop and bring that data into something like Microsoft Excel or Google Sheets and be able to do some analysis and graphing and averaging and things like that. So it's a way for me to store that data long term in a very easy way, programming wise. If I was to do this without a Gator log, it would be rather difficult and time consuming. And all of these culminate in the Gator Science Kit. So all of those boards we just talked about are in this kit together with a Gator Bit, Gator clips, an SD card and an SD card reader, so that right out of the box, this kit is ready to go in the science classroom for students to start building their own instrumentation, doing authentic science and computer science to really answer some of their inquiry questions. As always, we have some documentation that comes with our products. Each of the Gator Science boards has their own hookup guide that then points at their make code packages and some examples of how to hook it up. So from then on, we want to equip you and your students to be able to build and brainstorm different experiments of what you can measure in data that you can use to prove a hypothesis with. The Gator Science boards will be the focus of our third and final webinar series in the series, as well as probably highlighted in some future blog posts if you're looking for example projects. So please be checking our blog on a regular basis and log in for our third and final webinar if you're interested in this as a science teacher. Again, our next two webinars will be on the 16th, which will be simple circuits with the Gator boards. Again, I'm actually going to tackle doing an interactive diorama at a kind of a 5th, 6th grade level, based on maybe some mentor texts and reading some classroom reading. And then the next one on the 23rd will be a science exploration with the Gator Science Kit, where we'll take that and we'll look at a very basic instrumentation that you could build in the classroom. I'm gonna go put it out in the wild, and then I'll show you what I do and how I get that data onto Google Sheets. So both of those will be much more of I don't want to say interactive, but they'll be more build-oriented, project-oriented webinars. You'll probably see me and not just a slide deck. But for right now, I was just going to wonder if there are any questions by anybody that's watching currently. So question, do the Protos Snap boards break apart or do they have to stay together? They do break apart. In fact, I personally recommend breaking them apart because that makes them that flexible. We can embed them in different things. They do work put together or on that PCB substrate, but they can be a little difficult. So I actually recommend snapping them apart. And when you do snap them apart, remember, use some needle nose pliers. PCB can get a little sharp sometimes, so some pliers and maybe even a file to file down some sharp edges after you've snapped them out. Next question is, are there any existing lesson plans or activity guides? Yes, there are a few out there. So we have our existing documentation that each one has an example project and how to hook it up and some example code. But we do have a repository of projects on SparkFunEducation.com that you can use to start with. I am not completely sure if we have a bunch for the Gator boards, but we will be populating that more and more with Gator board specific projects as time goes on. And with that, I think that might be the end of the questions for today. Again, I'd like to thank you so much for joining me for this past 45 minutes or so. I hope you learned a lot about our Gatorboard ecosystem, at least some background and where it came from. If you are a person or a teacher that already is using the Gator Bit in your classroom or the Gator boards, please email me. We'd always love to hear how you're using them. Any input or feedback on how to make things better is also welcome. But more specifically, we want to know how these are being used in the classroom. So please reach out. Let us know what you're doing, and we'd be more than happy to share with the rest of the world what you're doing. So with that, thank you so much, and have a good rest of your day.